For an introduction, hi, my name is Gracelynne. I'm a rising sophomore at the Bridgewater Raritan High School, and today I'll be talking about cryptography, from even ancient ciphers to modern encryption. But before we get started, let's cover the LogStem Fun Math workshops. So currently, this is the fourth part of LogStem's Fun Math workshops. If you see any of the previous topics that you would be interested in, feel free to check out LogStem's YouTube for previous recordings. And if you would like to rewatch this one, you can also look for the YouTube, and you can keep up to date for any future workshops using LogStem's website. So let's just get started. Okay, so when we look at cryptography, we first want to start with some background knowledge. For starters, the definition of cryptosystems, which is a term I will be using, is the method for encoding and decoding. And the key is often a piece or pieces of information that can encode and decode information. Once again, I ask that if you are unmuted, please mute yourself so that it is easier for everyone else to listen. Now we get into the basic types of ciphers. Mainly in ancient times, there were two types: transposition and substitution ciphers. While substitution ciphers are pretty self-explanatory, where you are substituting letters, transposition ciphers involved rearranging letters based on a set system. Different ciphers have been used throughout time, since, as far as records show, ancient Egypt. Z, how would you be able to mute yourself, please? Okay, so popularized by the Greeks and Romans, ciphers continue to be present in our everyday lives, currently mostly in computers. Okay, so now we start from the beginning in the timeline. Some of the earliest ciphers were used by the Greeks, including the Skytail and the Railfence cipher, both of which are transposition ciphers. And I'll get to how they worked in the next slide. Okay, so for starters, the Skytail cipher involved wrapping a length of parchment around a cylinder, then writing across the twist of the cylinder, as you can see in the diagram below. And the main catch here, or the key, was that different cylinder sizes would yield different letter arrangements. So once you unwrapped the parchment, the letters would kind of be scrambled, and then you would rewrite it on a parchment. So then you would be able to send it to whoever would get the encrypted message. Next, we have the Railfence cipher, and the result is actually very similar to the Skytail cipher, but it is a bit more usable for those who maybe don't have a parchment and cylinder per se. This system involved creating n rows and then alternating the letters of the message between the lines, as you can again see in the diagram on the right. And the catch, or the key here, was that different numbers of rows would yield different letter arrangements. Again, different rows could actually correspond to different cylinder sizes, but this is more of a modern take on the Skytail cipher. So let's move on to our first example. So let's try encoding this message with k equals 3, or the key being 3, meaning that you create 3 rows, with the Railfence cipher. And the message is "meet me at the cafe." I'll give you about 3 minutes to work on it, and you can send me your encrypted message during that time. Okay, so now that it's roughly been 3 minutes,
你的名字讲的话，你把你的名字讲成那个，
if you would be able to mute yourself, thank you. Okay, so now I'll start going over how to encrypt this message. Okay, so given that there are 3 rows, we want to first create 3 rows, and then we evenly disperse the letters among these rows. And now this code actually does work pretty conveniently, where there are exactly enough letters to fit to each row. But of course, if there wasn't, you would just simply write any letters hanging afterward, like over here, over here. That part doesn't really matter too much. But then upon sending the letter, you would actually just send and upon receiving this message, one would use the key to first figure out what the 3 rows are, and then writing, my apologies, I think. Right, okay. And then writing this message across the 3 rows. So given that there are 3 lines, you would figure out, okay, so there are 15 letters in total, 3 lines. So every 5 letters, you would write that across the line. And then that would go on until you would be able to vertically read that the message read, "Meet me at the cafe." Okay, so does anyone have any questions on this cipher? Okay, if not, then moving on. Okay, so the earlier cipher was from the ancient Greeks, but now we fast forward to around 100 BC with Caesar's cipher. And this name is actually completely true. This was used by Julius Caesar in his own private correspondences with generals and commanders, usually during wartime. And what this code actually is a simple substitution cipher involving shifting the alphabet down a certain number of positions, aka the key again, and then replacing letters with their shifted counterparts. Even though back then, this cipher was a little difficult to decipher if they didn't know how the system worked, it's quite easy to decrypt nowadays, as computers can easily brute force out all 26 variations and then decide which one is legible and which one holds the message. But if you don't have a computer, one could technically also look at how often certain letters appeared, and then naturally trial and error the rest until they found the key. For instance, if in the English language, E is a very common letter. So if you saw a relatively uncommon letter like Q, you'd be able to use the E and Q shift and then try to shift all the letters, and then you would be able to technically reason out what the actual message was. So now I've basically finished explaining how this cipher works. And decoding is very similar, where you would just shift, if you shift down the alphabet a certain number of positions, while receiving, you would just shift the alphabet up a certain number of positions. Okay, so now let's move on to an example. Try encoding this message with the alphabet shift that I provided. The key is under the bench. Again, I'll give you around 3 minutes to try this one, and you can put your answer in the chat when you're done. Okay, so again, now that it's roughly been 3 minutes, we can start going over this one. And you can kind of see some types of variation in the chat, where sometimes, and this does happen in real life, where people choose to either keep the spaces or leave the spaces out. And I do believe my messages have some sort of lag, but as Charlie pointed out, for the rail cipher, the definition on the previous slide was different than the method on this slide. This was just a matter of preference. Usually this could be determined beforehand, but the idea is the same where you do alternate letters. Okay, again, if you would be able to mute yourself, that would be really helpful for me. Okay, so now we can start encoding this one as well. And I did have it pasted from earlier. So again, if you would be able to mute yourself, that would be helpful for me. Okay, so congratulations to everyone who got this code right. This is the actual encryption. And again, like I said earlier, to decrypt, you would just shift the alphabet back the other way, the same number of spaces from the original. Yeah, so to decode, you would technically, given this type of cipher where you could just write out the alphabet beforehand, you would see that W translates back to T, K back to H, and so on and so forth. Personally, I think that since you already do have the message written for you, it's a bit tedious to go back and retry. So let's just move on.
No, like I wanted to do like a different one, trying to decode a different one.
Oh, yeah, sorry. I didn't really have one planned for today, but you could definitely find some online if you ever wanted to in your free time. Yeah, okay. So if you have any questions, feel free to type them in the chat. Yeah, okay. So we can decode technically by finding the most common letter. I can redo my annotations from earlier. Yeah, so technically this cipher in itself is a very easy system to decode. If you did, for instance, keep the spaces. And you were left with like WKH more than once, you could reasonably infer that WKH is most likely the word the, because the is a very common word in the English language, or another word like and, for, and so on. Yes, people can steal secret messages. That is the point of trying to keep them a secret. And yes, if you steal a secret message, if it is encrypted well enough, then hypothetically the person who stole the message would not be able to decrypt it. Of course, back in the day, Caesar cipher worked a lot better than it does now. So I'm just going to go ahead and introduce another substitution cipher, unless anyone has any other questions. Okay, so if not, then moving on. Okay, so the next cipher we'll move on to is Vigenère's substitution cipher. This cipher in actuality is comprised of many Caesar ciphers with the alphabet shift, so the number of positions that you shift each letter by. determined by a keyword. And this concept is pretty confusing to explain in words, so I will go over an example in detail later. As a disclaimer, though, this cipher does involve modular arithmetic and just a basic understanding of mods, specifically mod 26 for the letters of the alphabet. Again, if you do have any questions on this cipher as I go through it, please hold until after I go over the example, as this substitution cipher is a bit difficult to explain in words. So first, we're going to choose a keyword and align it with the message. And for instance, if the message was 15 letters long and the keyword that you chose was 3 letters long, then you would just align it with the message 5 times. Then you would add the letters vertically, assuming that A equals 1, B equals 2, and etc. until Z equals 26. And then you apply mod 26 to the sum of the letters from the keyword and the message, and then find the letter aligning to the numbers mod 26 obtained from the previous step. So again, I felt that this one was called for more of a in detail example. So, okay. So our example is found the treasure as the message, and for a randomized keyword, I chose code. As a reminder, the keyword in all of these cases we have gone over so far is private, meaning that you would decide on this keyword beforehand with whoever you wanted to pass on the message to. So again, in this case, you would align the word code with found the treasure as many times as needed to cover the entire message. And then what we do is we replace it with the numerical value of each letter. And this is what I mean by that. So F is the 6th letter of the alphabet, C is the 3rd, O is the 15th, and so on and so forth. Of course, this method does take a little more time to both encrypt and decrypt, but it is more worth it as it is a bit harder to steal the information from. Okay, so after this step, you would add the letters vertically, and then also take it mod 26 at the same time. So for instance, 6 plus 3 is 9, 15 plus 15 is 30, but mod 26, meaning that 30 divided by 26 has a remainder of 4. So 30 mod 26 would be 4, and so on and so forth. Yes, to the question in the chat, if the number of letters in the keyword isn't a factor of the number of letters in the message, then we would just stop in the middle of the word. So you would technically just have the word hanging. Yeah, okay. And then after you found the sum, you would replace it again. So 9 is I in the alphabet because I is the 9th letter, and so on again. And so technically you would just pass on this last line. And then the question arises, how do we decrypt this kind of message? So to kind of explain it a bit in detail. So you can originally, you know that this is the message you're given, this is the numerical value, and you have also decided on the code beforehand. So then, knowing that you technically would know all of these pieces of information, you would be able to subtract 9 from 3 to get 6, 4 from 15 to get 15, mod 26, and so on and so forth until you ended up with this row, which you could then pass to these letters. So just for sake of time, I'm not really going to have an example for you all to try out, but if you have any questions on the method, now would be the time to ask. Right, okay. So how do you go from 4 and 15 to 15 again? So technically you would be doing subtraction, mod 26. If you haven't learned it yet, that's totally fine. But basically, you would have 4 minus 15, which is technically congruent to 15 mod 26 if you've seen this notation before. I hope that answers your question. Okay, so great. Moving on then. Now we'll go on to a lot more of a famous and well-known cipher known as the Pigpen Cipher. So just for a bit of historical background, this cipher was used by the Freemasons secret society in the 1700s, as well as by Union soldiers imprisoned in Confederate camps during the American Civil War. So this cipher did have some level of anonymity from the 1700s to the 1800s before it was eventually cracked and well known to the public. So I won't have an example for this one because I don't really see how you would be able to type in symbols to me. And also encoding and decoding are relatively easy. So on the left here, these diagrams show how each of the symbols on this side arise. So for instance, A is surrounded by a line to the right and to the bottom of the letter. And that is how you get that symbol. And the dots are to distinguish this graph from this graph because there are 26 letters that you need to cover. Okay, so again, I believe that this symbolic cipher is relatively easy to understand. But if you do have any questions, feel free to ask. Okay, so for now though, I will move on. Okay, so now we fast forward from around the 1700s and 1800s to the early 1950s, give or take, and early 2000s. So one of the most well-known forms of encryption is RSA encryption. And this is a public key encryption tool based on the idea that multiplying large numbers is relatively easy with computers. But factoring large numbers, even with computers, is difficult and also time consuming as you can only just brute force. And okay, so going over what this really means, public key means that part of the key is actually accessible to the public. So part of the key is private, but also half of it is public. And I'll go over the relative concept of this idea using this diagram. Okay, so let's assume that Bob is the person who wants to receive messages in this case, and Alice is a person who wants to send Bob a message. In real life, Alice also represents the general public, or Bob's customers usually, and attackers is also part of the public, but just anyone who has malicious intent and wants to steal messages. So how Bob can technically let anyone send him messages is to put an open lock and a box out there. And now we're just going to only talk in the context of this example, but let's just say Bob sends this box and open lock to Alice. And the diamond is a message or just a diamond that she wants to send to Bob. So taking Bob's box and lock, she can put the diamond inside the box, lock the box, and then send the box back to Bob. And he's the only one who has this golden key to unlock the lock. And note that anyone can technically steal this lock and key for themselves, but if there's nothing valuable inside, then it's not really worth stealing. And that's how Alice can safely send Bob this diamond. Okay, so that is the overall concept of RSA and public key encryption. Does anyone have any questions on this idea? Okay, yeah. So in the concept of this diagram because I will get to the more math side of it later. The lock is, in this case, just a normal lock, like a lock and a key, the type you've put maybe on a suitcase or on a locker. If the attacker gets the key, well, the idea is that the attacker wouldn't be able to directly steal the key, especially in RSA encryption, and I'll get to this soon. Yeah, so if there are any other questions, though, I can answer them now. Okay, so if not, I'm just going to move on to the next slide then. Okay, so this is quite a bit of information, but I'm going to try and explain it as clearly as possible. Note that I did try to color code this slide, and the green is everything that is public and or derivable by public information for the most part, and D is the private key, meaning that only Bob in this case would have this information. Okay, so first we start by having the receiver of the messages, Bob, choose two large primes P and Q. And by large primes P and Q, this is a prime that's somewhere between 2048 and 4096 bits long. And then they will multiply this P and Q to get N. And this is actually part of the key that is available to the public. And then the receiver will calculate the phi of N, which is basically just P minus 1 times Q minus 1. And then choose a number E that is actually relatively prime to the phi of N. Again, E is available to the public, so it is commonly just 2 to the power of 16 plus 1, but it can also be a lot smaller, like 3, just because in the case of E, security is not an issue. And then the receiver will calculate the modular inverse D of E mod the phi of N, which again is P minus 1 times Q minus 1. And this modular inverse is actually the private key. If you don't know what the modular inverse D of E means, that basically just means D times E is congruent to 1 mod the phi of N. Okay, so moving on. Then we come to the issue of transmitting the message. So the sender who wants to give Bob the message will convert their message into the number M. And this is commonly using the ASCII alphabet, which is prevalent in coding, if you've heard of it. And then the sender will calculate C, which is congruent to M to the power of E mod N, where C becomes the encrypted message. And technically, attackers can still steal C, but the idea is that they're not able to then decrypt this message. But when the receiver of the message gets it, they can compute C, again to the power of D, which is congruent to M, which is the original message, mod N, and then retrieve the original number M and convert it back to letters because they know that they're going to use the ASCII alphabet. Okay, so does anyone have any questions on these two slides? Yes, I will get into an example briefly, but only for generating the public and private keys, just because actually using the encryption method is a bit more difficult and will probably take more time than we do have today. Again, usually this is all done with a computer. So I did also, for the example, choose small primes to work with. Okay, so if no one has a question on these two slides, then we can just move on to the example. Okay, so again, if you have any information that you would like me to maybe repeat, you can send it to me in the chat. But I'll give people like roughly just 2 minutes to kind of think about what they would do with these two primes that I've chosen. And also you can send me any of the values you get, like N or E or D, as these are parts of the actual keys that you'll be generating.
I don't get it.
Okay, yeah. So which part don't you get?
Like wait, like what type of alphabet is it?
Okay, so the type of, it's an alphabet you'll commonly see in coding. So each value of the alphabet, lowercase and uppercase, will kind of have like their own values. For instance, I think I only remember 2 of the current values in the RSA alphabet, but I do know that H is equal to 72, I believe, and then I is equal to 73. And obviously you can deduce the rest of the alphabet from there, but these are the capital versions. Yeah, the alphabet is something you could easily search up. There is a table, like a standard for a table that you will be able to see if you search it up. But yeah, and then you would kind of translate it to binary, because this is what a computer does when it's using RSA encryption. Does that answer your question at all?
Yeah, but I don't really remember exactly how you're supposed to do it. There's like so many steps.
Yeah, okay. So yeah, I can probably just move on to actually doing this then. Yeah, unless there's any more questions about the concept or like any of the steps and like how they work. I did forget to mention this earlier, but sorry. This works because of Euler's theorem, that C to the power of the modular inverse will then be congruent to M, which is the message. But okay, so going back then. Okay, sorry, that was a bit too far. Okay, so first we want to find N. Remember that N is the product of P and Q. And then N is equal to 3 times 5, which is equal to 15. Okay, so as you saw from earlier, that little peek, the next step is a bit more word heavy, but I'll try to explain it to the best of my ability. Okay, so now our main step is to find the phi of N and choose an E value. And then note that once we find N, the phi of N, E, we can also calculate D, and then that will actually be all of our keys that we need to actually be able to send messages hypothetically. Okay, so from earlier, we know that the phi of N is P minus 1 times Q minus 1. So in this case, it would be 2 times 4, which is equal to 8. And a number relatively prime to 8 is 7. This is just an arbitrary number. And now that we have our public keys, we can find our private key, again, which is D. This is the modular inverse of 7 mod 8, which coincidentally happens to also be 7. So as a recap, we would have that N equals 15, E equals 7, and D also equals 7. Okay, so again, as like a general disclaimer, these primes will never be this small. If they were this small, people would really just be able to look at the code and then be able to almost decrypt it immediately. But again, the current largest prime I think that is known is like 24,800,000 something thousand digits, meaning that there are very large primes in this world. And also RSA had a history of using 1028 bits, and that was actually shown to be able to be brute forced by the strength of computers, which is why now it's 2048 to 4096 bits long. but P and Q again are just a very small example. Okay, so does anyone have any questions on generating RSA keys? Oh, okay, yeah, I see the question. Are different bits digits? So actually, no, different bits are not digits. A bit is either 0 or 1. Just keeping in mind that computers do communicate and operate in binary. So technically, yeah, like I said earlier, actually, H equals to 72, I think it is, would actually then be converted to binary. Yeah, if that makes more sense. So what I mean by like 2048 bits would just mean like around 2 to the power of 2047, between that and 2 to the power of 4095. Okay, so how do you decrypt it? Right, so I can go to my previous slide. Okay, so decrypting is actually just in the third step in this case. Upon receiving the message, the receiver would compute C to the power of D, which by Euler's theorem is congruent to M mod N. And if you don't know what Euler's theorem is, feel free to search it up online. But yeah, that's kind of it in that case. And what is the modulo inverse? Okay, I can go back one more slide. Okay, so if you don't know what modular arithmetic is yet, this might be a bit more complicated of a concept, but basically assume that the modular inverse is denoted by D, and we're trying to find the inverse of E mod the phi of N. So D times E, you're trying to find the value of D, where D times E is congruent to 1 mod the phi of N. And D will be somewhere between, I believe, 1 or 2, all the way up to the phi of N minus 1. Yeah. So does anyone have any other questions on RSA encryption?
Can you go back to the like page you were on, like before you went 2 pages behind? Like I have a question about that part.
So like with the explanation and everything?
No, like wait, what? Like just go there. I'll explain.
Okay, just like tell me when to stop.
Like I think, yeah. Like what does RSA stand for?
Okay, so RSA actually stands for the names of the people who came up or proposed this encryption method. I can briefly search it up just because I don't remember the names too well. Okay, so RSA stands for Revest Shamir Adelman. And there's actually kind of a backstory behind why it's RSA and not ARS, which is usually what it would be with alphabetical order. So back then, RSA was not like very famous, and they didn't think it would like become so common in the world. So actually, Adelman, who was one of the contributors, felt that he didn't do as much as Revest and Shamir. So he actually let his own last name be last in like the list of contributors to this. So that's why it's called RSA actually. That's kind of just like a bit of, again, historical background, but yeah. Are there any other questions? Okay, so if not, then I'll just move on. Okay, so this will kind of be the last thing I talk about for today. Right, yeah, what I said in the chat are the 3 names of the contributors. Okay, so as more encryptions are introduced, the amount of attackers will of course increase as well due to wanting to know the sensitive information that is usually passed in them. As a result, the field of cryptography is constantly evolving, and currently some of the industry standards include the Advanced Encryption Standard, also abbreviated as AES. This is actually used by the US government and many other powerful organizations. This is a private key encryption, by the way, as well as, again, like we talked about earlier, RSA and two-fish. And actually, RSA did have data breaches in the early 2000s, but that was only in instances where the primes chosen were only like 1028 bits long. So basically, it wasn't long enough, and the computers were able to brute force out what the primes were. And then they were able to kind of receive all the information that was on that channel. And these methods, so RSA, two-fish, and AES, were actually all proposed to replace the original data encryption standard. And this was like the first major international standard. Now, data encryption standard is actually rendered more or less useless because computers have been shown to be able to basically hack kind of anything that uses this standard. So new encryption methods continue to be proposed and designed, tested to create safer, less hackable methods for passing information. And again, the reason why the field of cryptography continues to evolve so quickly is because computers will also get stronger and faster, and they will be able to use brute force to kind of figure out everything a lot quicker, just like back when data encryption standard was the international standard. Computers were, of course, a lot slower than they are now. And that kind of leads to the reason why now advanced encryption standard is used. Eventually, these will definitely become obsolete, but as for now, they are not like, I mean, they technically can be brute forced, but the idea is that brute force would take most likely years to even decades to actually decode, up to the point where like the information is basically irrelevant. So kind of 2 examples I can think of off the top of my head for that would be like, okay, if you were to send a message during wartime and it took like 3 years to actually be able to brute force out this message, then whatever you're sending might have already happened and they don't even like know what they're sending. So it's not worth the amount of effort it would take to actually decode these messages in a reasonable amount of time. Another would be like if you're passing credit card information and it would take like 2 decades to actually decrypt the credit card number and like all the personal information. By that point, the credit card number might have already expired and it would be useless. The hacker wouldn't really be able to use anything. And that's kind of why cryptography works, because computers can brute force, but maybe not fast enough for the information to be useful. Okay, so that is the last topic I will kind of touch upon in today's workshop. Again, this is only part 4 of the fun math workshops held by Logistem. There are many other parts that you would be able to register for, like you did this one, on the Logistem website. And that's actually it for today, and thank you for attending. If you still have any residual questions on anything I went over today, feel free to stick around and ask, but otherwise, thanks for attending.